Hello students, in the last lecture we defined the derivative, but we haven't done any examples and haven't defined any rules. So we're going to do it in this lecture. The first example that we're going to do wants us to find the derivative. So let f of x to be equal to 4x minus 3, compute f prime of x. So in other words, we have to find the derivative of f of x. So let's do this out. The definition of the derivative says the following. If you want to find the derivative, you have to find the limit when delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. So we have to implement it for this function over here, and my strong suggestion, always start with this definition first, and this will help you to do the problem right. So let's do this out. So what is f of x plus delta x? F of x plus delta x. So what we need to do, we have to take x plus delta x and plug it in over here for this x. So we open parentheses, we say 4 parentheses x plus delta x minus 3. So we figure out f of x plus delta x. Then we put a minus. On the bottom we will have delta x. And what is f of x? F of x is actually this expression over here. Look, that says f of x equals 4x minus 3. So we open parentheses, we say 4x minus 3. And this set of parentheses over here is a crucial step, because if you miss them, then your problem will not be right. So we have limit delta x goes to 0. Delta x goes to 0. We open up the parentheses for the first expression, and at the same time, we're going to multiply both expressions by 4. So it's going to be 4x plus 4 delta x minus 3. Then this minus, it's like multiplying by -1, so it's going to be negative 4x. And then this minus and this minus, if we multiply them together, we're going to get positive 3 divided by delta x. And what do we know? We know everything after this minus should go away. So let's think. 4x with the minus, 4x with the plus. So we can add this to 0. This positive 3 and this negative 3, we can add up to 0. So what's left in the numerator? In the numerator, we have 4 times delta x divided by delta x. And I forgot to write my limit, so that's a big mistake. So we have equals limit delta x goes to 0. So we have to tell ourselves that we can divide by this delta x. So let's look. Delta x goes to 0 for the limit, means it will never be 0, but we can divide by this delta x. We're left with the limit delta x goes to 0 of 4. And we know that the limit of a constant is constant, as you can see. As you can see that in here we don't have the word limit anymore because we calculated the limit. And this would be actually the answer for our derivative. So derivative will be equal to 4. All right, so we solved this example, and we can state this example as a theorem. So theorem, or just a rule, says that if f of x is equal to mx plus b, so it's a straight line with a slope m, then the derivative is equal to the m. All right. So this would be the assignment for your homework. So prove it, and we're going to discuss it in class if you cannot do that. But in a simple words, it tells you if in a simple words, it tells you if you have f of x equal to -1/2 x plus 3, f prime of x is equal to -1/2. So you take the slope, and that's your derivative. So we don't really need to evaluate it through the definition one more time. So next rule is about constant. So what's going on if your function is a constant? If f of x is equal to c, where c is a constant, and c is a constant, then derivative of this function is going to be derivative of a constant is going to be 0. Graphically, it's really easy to understand because if you draw a straight line, you will see that it's a horizontal line through point C, and so its slope is 0, right? But we want to use the proof by definition. Proof, it will go by definition. All right, let's do this. So definition says f prime of x is, as I said before, I always recommend to start with the full definition. Limit when delta x goes to 0, f of x plus delta x minus f of x divided by delta x. And that's our definition. So let's try to use it. So what would be x plus delta x? Our function is c, so no matter what you're going to plug in into c, it's just going to be c, right? So we'll get c for the f of x plus delta x because there is no really x to plug in. Then what is f of x for this part over here? It's also c. And on the bottom we have delta x. So we have a limit of 0 over delta x when delta x approaches 0. But delta x approaches 0 means it will not be equal to 0. So it's some kind of a number which is not 0, right? So we have 0 over some number, so it's just 0. So we have a limit of 0 when delta x approaches 0. But 0 is a constant, so we get 0. So we proved this theorem. So we're done with it. All right, so small example would be just to understand what we're talking about. Small example. What is the derivative? Or maybe let f of x be equal to 7. Find f prime of x. So the solution is very short and simple. F prime of x is equal to derivative of 7 is equal to 0 because it's a constant. It's a really nice theorem. All right, so the next rule is tiny bit more complicated, so let's do this. If y is equal to f of x is equal to x squared, then f prime of x is equal to 2x. So let's try to prove this rule. Again, by definition, we know that the limit of delta x, not the limit, but derivative is equal to the limit. So I should start with the derivative. Derivative of f is equal to the limit when delta x goes to 0, f of x plus delta x minus f of x over delta x. So let's plug everything in. We have limit, delta x goes to 0. Let's calculate this quantity over here. We have to take x plus delta x and, mistake, and plug it in over here for x. So let's do this out, parenthesis, x plus delta x quantity squared minus f of x, and f of x is just x squared divided by delta x. So what do we get? We get limit delta x goes to 0, and then we have to use our famous formula for the sum of the square of the sum, square of the sum. So it's going to be first term squared plus 2 times the first term times the second term plus the second term squared. And then we have minus and we have x squared. On the bottom we still have delta x. So what can we say? The hint is the term after the minus should go away, so this negative x squared and this positive x squared adds up to 0. We're left with the limit delta x goes to 0. We have 2x delta x plus delta x squared divided by delta x. And as before, we're going to factor delta x out, so it's going to be limit delta x goes to 0. We factor delta x out, 2x plus delta x, that's what's left. Let's see if we did it right. This delta x is over here, so there is only 2x. And one of those is also outside, so we have delta x. Now we have to convince ourselves that we can divide by this delta x. And again, only because we have this limit over here saying that delta x goes to 0 but not equal to 0, that's what allowed us to divide. Finally, we have limit of delta x goes to 0 of 2x plus delta x. And by the direct substitution, if we plug in delta x equals 0, this term will be 0, and our answer will be 2x, and that's what we wanted to show. But if you remember, we got this answer in like our third week of class. So we've done with this exercise, but let's do a short example for this theorem that we just proved. The assignment says find the equation of a tangent line, maybe of the tangent line, and here probably an equation. Find an equation of the tangent line at x equals 3 for y equal to f of x equal to x squared. So let's do this out. We know that m, which is the slope of a tangent line, is equal to the f prime at 3, is equal to f prime at 3. So that means we need to find the derivative of f, and then we're going to plug in 3 into it. So we need to find the derivative of x squared, and we already showed in the previous theorem that this is going to be 2x. So now we have to find the slope, so it's going to be, to find the slope, we're going to take f prime and evaluate it at 3. So it's going to be 2 times 3, which is 6. So we have the slope, and but as you remember, we need to choose which form of the tangent line we're going to use. I'm going to use point slope equation, which says y minus y1 equals mx minus x1. We have x1 equal to 3, but y1 we don't have. So to find y1, we have to calculate f of 3. So we're taking our value x, we're plugging it in into the function. So it's going to be 3 squared, which is going to be 9. So now we're ready to use the equation. We say y minus 9 is equal to 6 times x minus 3. And this is the equation of the tangent line for our function. All right, so next topic that we need to discuss is a small definition, just mostly for convenience. So this definition is for convenience purposes. So let's see what it is. It is saying that f of x, f of x is differentiable if and only if and only if f prime of x exists. So basically, we call a function differentiable if the derivative exists, and vice versa. If f is differentiable, we have the derivative of the function. I think just an easy way to call something, instead of saying that you have a derivative of the function, you can just say the f is differentiable. All right, so the rule that we're going to discuss next is the following. If f of x is differentiable and g of x is equal to k times f of x, we just have to mention what k is, where k is a constant, then g of x is differentiable and g prime of x is equal to k times f of x with a prime sign. So again, it's a constant multiple rule, but for derivatives, before it was a constant multiple rule for the limits, but this is a constant multiple rule for the derivatives. So it tells you that if you have k inside of the derivative, you can always take it and put it outside. So let's try to prove this rule. Okay, so what would be the proof? So we're given that f prime of x exists. Why? Because it says that f of x is differentiable. But if f prime exists, we have that f prime of x is equal to the limit of f of x plus delta x minus f of x over delta x, and delta x approaches 0. So what does it tell us? It tells us that we can calculate this limit exists, so everything is fine with this expression because f is differentiable function. So now we're going to consider g of x, which is equal to k times f of x. And we're going to build the derivative for this function. So we have g prime of x equal to limit when delta x goes to 0, g of x plus delta x minus g of x over delta x. So we use the definition. Now we're going to take this x plus delta x and we're going to plug it in over here for x. So we have limit delta x goes to 0, and we plug everything in. So we have k, then we have times, then we have f of x plus delta x. So we plugged in x plus delta x into the g function. Then we put a minus, and we put g of x. And g of x is just k times f of x. So on the bottom, we put delta x. We move to the next line. So let's look at this expression carefully. We have k over here, and we have k over here. So it's a common factor, so we're going to factor it out. We're going to put it outside, and inside we have f of x plus delta x minus f of x divided by delta x. Again, if the k is outside over here, then minus, and k is outside over here, and we have f of x at the end. Everything is correct. And according to the previous theorem, we can take not the previous theorem, sorry, I made a mistake. According to the rules of the limits, if we have a constant inside, we can always put it outside. So we use constant multiple rules for the limit. So what's left inside? Inside we're left with f of x plus delta x minus f of x divided by delta x. But this is exactly the definition of the derivative of f, right? Look, this is exactly this expression over here. So final step is we write s prime of x, and this is our g prime of x, g prime of x. So we prove the rule. And that's really good for us, because now we can take constants and put them outside. Let's do a short example. We're going to do longer examples when we're done with most of the rules, because it would be more interesting. So the assignment says find the derivative of f of x equals to 5x squared. Now let's try to do that. Solution. So we calculate f prime of x, or 5x squared. Derivative sign, 5 is a constant, so we put it outside. We're left with the derivative of x squared, and derivative of x squared, as we learned before, is 2x. Finally, we have our answer, which is 10x. And we solve this example by using the constant multiple rule. So next rule is the addition rule. So let's do this one out, the addition rule. So our theorem is a little bit longer than before. If f of x and g of x are differentiable, then h of x, which is f of x plus g of x, is differentiable. But not only it's differentiable, but we can also find its derivative. So we say h prime of x is equal to f prime of x plus g prime of x, and this is a sum rule. But if it's a sum rule, it's also a difference rule. So sum or difference rule. All right, so let's try to see how do we prove this result. So given f prime, given f of x is differentiable, we have f prime of x is equal to the limit when delta x goes to 0 f of x plus delta x minus f of x over delta x. Because the function is differentiable, this limit exists. And given g of x is differentiable, we have g prime of x equal to the limit delta x goes to 0, and we have g of x plus delta x minus g of x divided by delta x. So this is only given from the statement of the theorem, from this statement. Now we're going to consider h prime of x. And h prime of x, by definition, is the limit delta x goes to 0. I don't need that big of a line here. So what is it by definition? By definition, it is h of x plus delta x minus h of x divided by delta x. So let's try to plug everything in. So we have limit delta x goes to 0, and we need some space here. So what is h of x plus delta x? Remember, h was f of x plus j of x. So if we want to calculate h of x plus delta x, we would need to take this x and put x plus delta x instead of it, and the same for this x. So we open parentheses, we have f of x plus delta x plus from here, then g of x plus delta x, then we put a minus, and we write h of x over here. So the minus is here, then h of x is f of x plus g of x. And the whole thing is divided by delta x. So what we're going to do, we're going to distribute this minus through the expression. We're going to get limit delta x goes to 0. We have f of x plus delta x plus g of x plus delta x minus f of x minus g of x divided by delta x. And what I'm going to do, I'm going to combine together f and g's. So we have limit delta x goes to 0, f of x plus delta x minus f of x plus g of x plus delta x from here minus g of x divided by delta x. And we know if we have two fractions, if we have a over b plus c over b, we can write it as a plus c over b. But also, if we have a plus c over b, we can always write it as a over b plus c over b. So that's what I'm going to do over here. I'm going to write the first expression with f's over delta x plus the second expression with g's over delta x. So let's do this. We have limit delta x goes to 0. We have f of x plus delta x minus f of x divided by delta x, then the plus, then g of x plus delta x minus g of x over delta x. And this is the limit of the sum, and we know the limit of the sum is the sum of the limits. We have limit when delta x goes to 0, f of x plus delta x minus f of x over delta x, that's the first one. Then the limit when delta x goes to 0, not really accurately here, so a little bit more accurate. Delta x goes to 0. And we have g of x plus delta x minus g of x over delta x. but this is exactly the definition of f, the derivative of f, and this is exactly the definition of the derivative of g. So we have f prime of x plus g prime of x, and that's what we wanted to show. So this proves this theorem, right? So that concludes this theorem. So we're done with this theorem for the sum. There is no real good example for this. Again, we'll try to do bigger examples when we learn more rules. So let's do the next rule right now, and then probably the last one for this lecture. This rule says if f of x is equal to 1 over x, and x is not equal to 0, because if you use 0, you will be dividing by 0, not really good, then f of x is differentiable. Differentiable means you can find derivatives, but not only that, we're going to actually show what the derivative is. Derivative of 1 over x is negative 1 over x squared. And we'll try to establish this result. So let's try to do that. We'd like to show the derivative of 1 over x is negative 1 over x squared. And the only tool we have for now is the definition, nothing else. So we will do that. We'll say that f prime of x is equal to the limit when delta x goes to 0, f of x plus delta x minus f of x divided by delta x. So it's a limit when delta x goes to 0. So let's try to calculate it. Over here, instead of this x, we're going to plug in x plus delta x. So it's going to be 1 over x plus delta x, then minus this minus, then f of x, which is 1 over x. 1 over x delta x. And then we need to evaluate it, and you can clearly see that if you plug in delta x, it wouldn't work because you would get 0 on the bottom, so it wouldn't work. So we need to simplify the numerator. And let's do this. Delta x goes to 0. My arrows are not really good. We have delta x, so we create a common denominator. So first fraction has x plus delta x, and so we want to introduce x over here. So we're going to write x and x. Then we're going to put a minus. Then we have x over here, so we want to introduce x plus delta x. So we're going to put it here. But since we put it into the denominator, we're going to also put it into the numerator. So we have limit delta x goes to 0. We don't touch denominator. In numerator we have, look, this is a common denominator, so we'll write x times x plus delta x. And since we have a common denominator, we're just going to take and multiply 1 by x. Then we're going to put a minus, and we're going to distribute this minus through this expression. So it's going to be minus x minus delta x. And we can see that this x and this x, they add up to 0. And also, instead of thinking about this number as delta x, we can think about it as delta x over 1. We move on to the next line. We write limit when delta x goes to 0. Then what's left over here? There is a minus, there is a delta x. On the bottom, we have x times x plus delta x times the reciprocal of this expression, which is 1 over delta x. And we have to convince ourselves that we can divide by this delta x. Again, we've done it many times already. Delta x goes to 0, but not equal to 0, so we can't do that. Let's see what's left. We still have the word limit again. while we're not done with the limit, we should write the word limit, but as soon as we're done with the limit, it shouldn't be there as a word. All right, so what's left? We have minus 1 in the numerator, 1 and minus. In the denominator, we have x times x plus delta x. So let's try to use direct substitution on the side. Direct substitution tells you minus 1, x, then x, and instead of delta x, we're going to plug in 0. So let's calculate. X plus 0 is x, and x times x is x squared. So we get negative 1 over x squared, which is what we wanted to show, right? So we're done with this theorem. And to finish this lecture off, small example. Let f of x be equal to 3x squared minus 2 over x. Find f prime of x. So we would like to find the derivative of this function, 3x squared minus 2 over x derivative. So since there is a minus in between, we can split it up and write it as 3x squared derivative minus 2 over x derivative. So we use the sum difference rule. Sum difference rule, very useful. We used it here. Now we have a constant 3 over here, so we can move it up front and write x squared derivative. X squared derivative minus, and 2 is a constant, so we can move it up front, so we're left with 1 over x derivative. Then we have 3, and we apply the rule for x squared, which is 2x, then minus 2, and we apply the rule for 1 over x, which is negative 1 over x squared. And if we simplify it, we're going to get 6x if we multiply these two numbers together. And negative 2 times negative 1 is positive 2 over x squared. And this would be our answer for this exercise. And we will do a few more in the next class, in the next lecture, and in your homework. And I'll see you in the next lecture.